Welcome to my channel Fee Concepts CHM. This is the first part of the series of Introduction to Optical Fibers, where we will see the introduction part and about the total internal reflection. In short, we will call it as TIR. Introduction. We have seen or we have studied about lasers. You can refer to the playlist of lasers to understand the principle and working of lasers. So with the development of lasers, another field has emerged which is called as fiber optics. So the optical fiber is being used in the field of communication systems to transmit data from one place to another. Fiber optics is used to transmit voice data, video data, or digital data. This data is transmitted using light signals, and so fiber optics is a technology in which the data is converted, which is an electrical signal. The data which is an electrical signal is converted into optical signals, and they are sent through a thin glass fiber, and again at the other end this signal, the light signal, is reconverted into electrical signals. So to have an efficient communication system, the data that is carried by the light waves, they need a guiding medium through which it can be transmitted safely, and this guiding mechanism is called as the optical fiber. The communication through optical fiber is known as light wave communication or optical communication. Total internal reflection, in short we will call it as TIR. We have learned about refractive index in optics. It is a dimensional number that describes how light propagates through a medium. We know the relation between the refractive index and the velocity. The formula is n is equal to c by v, where c is the speed of light in vacuum, v is the phase velocity of the light in medium. So like if for example, refractive index of water is 1.33, that means light travels 1.33 times faster in vacuum than it does in water. Refractive index determines how much light is bent or refracted when entering a material. We know the famous Snell's law, which gives the ratio of the refractive indices of two mediums. N2 by N1 is equal to sin I upon sin R. We can see here two mediums, one is air and glass. Here the light is incident at an angle I. So I is the angle of incidence with respect to this normal. This is the normal. And R is the angle of refraction when light comes out into the air. So this is the medium or the interface between the two media with refractive indices N1 and N2. So we have written down the Snell's law in the earlier slide, the same formula we use. Now, if I is equal to theta c is called as a critical angle. So for if I is equal to theta c, for which the angle of refraction is 90 degrees. So the angle of incidence when it is equal to critical angle when the angle of refraction is 90 degrees. So we can write down sin R as sin 90 degrees, and that is equal to 1. If you substitute this Sin r is equal to 1, in the Snell's law, we get n2 by n1 is equal to sin I. You can replace this I by theta c. I is equal to theta c. So n2 by n1 is equal to sin theta c. Now, if I is less than theta c, we are considering here again two medium, glass which has a higher refractive index and air which has a lower refractive index. So this is the denser medium and this is the rarer medium. So when I is less than theta c, the ray will refract into the rarer medium. So if we consider this as a normal, we can see that the ray is refracted into the rarer medium. So light is incident through the glass and it comes out into the air. So refraction takes place. So this is ray 1. Same way as you change the angle of incidence, this way the ray is refracted. As you increase the angle of incidence, the ray, you can see it is bending away from the refracted ray is bending away from the normal. If I is equal to theta c, then the ray just grazes the interface of the rarer to denser medium. So that is shown by this black ray. So here the angle of incidence is equal to theta c. So the ray is going just along the interface. This is ray 2. Next, when I is greater than theta c, then the ray is reflected back into the denser medium. So as you go on increasing this angle of incidence with respect to the normal, as you go on increasing, when the angle of incidence is equal to theta c, the ray is not refracted but it is just moving along the interface. It is just grazing the interface. And when the angle of incidence goes above the critical angle, the ray is not refracted outside but it is returned back into the same medium, into the denser medium. So this is ray 3. Same way, as you go on increasing the angle of incidence more than the critical angle, the ray is reflected back into the denser medium. So critical angle is the angle of incidence for which the angle of refraction is 90 degrees. When the refracted ray exceeds 90 degrees, it is not refraction anymore. Instead, the light is reflected back into the same medium it started from. And this phenomenon is known as total internal reflection. So total internal reflection is a phenomenon which occurs when a propagated wave strikes a medium boundary at an angle larger than a particular critical angle with respect to the normal to the surface. So we have to note here that this phenomenon PIR happens for a light traveling from a denser medium to a lighter one. And the another condition that is to be fulfilled, one condition is this, that the light should travel from denser to the rarer medium, and the another condition is that the critical angle or the angle of incidence should be equal to the critical angle. When the angle of incidence is equal to or greater than the critical angle, then TIR will occur. Beyond the critical angle, 100% of the incident light is reflected back into the same medium. Thank you for watching this video.